Hi, welcome back to our loveliness here. There we go. That is chapter 2. And so we're in section 2.6, and we're going to be talking about the periodic table. And what's really cool is that when we're looking at the periodic table, this is Mendeleev's original kind of notes about how the elements would be arranged. And if we look at, getting rid of my pen here, hopefully. If you've never seen a TED Talk, they are really a good thing. But TED Talks, this one kind of dwells into this problem. And so then it will go and talk about thinking, watch the video. Then we're going to think about which of the following elements is not easily spotted by ancient cultures. And we'll talk about why. And then digging deeper, there are some additional resources on this particular subject. So what you'll want to do is, of course, watch the YouTube video on Mendeleev and how the periodic table was actually put together. Because I'm going to ask you questions about this on the test. Okay, but we're going to go back to our PowerPoint here. And there's another link down here, the crash course. And that does go through the periodic table also in terms of how it was arranged. And the really cool thing about Mendeleev is that he arranged his periodic table by atomic weight, the mass, even though he didn't have a mass spectrometer to say what the mass was. We know it as the atomic number, the number of protons. And what he did is he actually said there were going to be some elements in here that had certain atomic numbers, but he had no idea what they were. And so he was predicting elements according to this periodicity, this behavior, periodic behavior, that there would be elements in these gaps yet to be discovered. And so he was actually right about this. And so our modern periodic table stems from him. So here's our periodic table. And any horizontal row is called a period, and any vertical column is called a group or a family. Now, you do need to know some special groups. This is group 1, and so it says 1A above it on the periodic table, and then we'll have 2A, and then we have 3A, 4, 5, 6, 7, and 8. And they'll all have the letter A behind them. And some of them actually, the group names are special. For example, the alkali metals, which we'll talk about in a little bit of detail. Then we have the alkali earth metals, okay, and this should be alkaline. So alkaline earth metals. Sorry about that, did not get all that smushed on there. We also have the halogens and then the noble gases. Now, this is the periodic table that is posted in Canvas. This is the actual periodic table that you get for the exam. And you're going to notice that some of the names, like here, this is krypton, capital K-R. The name is not scratched out, but it is for some of the elements. And that's because I want you to know the first 20 elements, so numerically by atomic number, the very first 20, okay? So we're going to have to know all of these guys. Their symbols and their names. So we have to know that H is hydrogen, okay, the element hydrogen. And spelling will count on the names. So know the first 20 elements and then also the following list. So we have titanium, vanadium, chromium, manganese, iron, copper, cobalt, nickel, copper, zinc, cadmium. This is tin, this is lead, and this is mercury. And so you need to know those because we're going to be seeing those elements quite frequently. And so it's nice to know their isotopic symbols. And it's usually the first letter in their name or the first couple of letters in their name. Some of them won't be, though. For example, copper is Cu, not Co. And that's because it's from cuprium, which is the Latin word for copper. And so some elements like lead is Pb from plumbum. Again, the Latin word for lead. So Some of them won't have symbols that are intuitive. But you do need to know these, and these can be on any quiz or exam from now on. Now the alkali metals are going to be that very first column in our periodic table, okay, our very first vertical column. And what we'll see is they are all metals. They're all gray and shiny, and they're soft, so you can easily cut them with a knife. And so what we'll see with these metals is that if we look at how they behave, and I always like doing this demonstration. So in water, oops. Sorry about that. We got our commercial here. Let's go back. Because I messed it up and I touched it. There we go. So you're going to see that the sodium metal floats around on the top of the water, and notice that it has ignited, and the flame here is orange. And so normally a metal would sink, but it is not. You're going to notice that we get some movement over here, or some solution is getting cloudy, the water is getting cloudy, but this shows sodium in water, and this is very reactive. Now if we were to take potassium in water, potassium of water is going to get a little bit bigger. So if we were to look at this explosion, and we're going to look at our alkali metals here, whoops, I did not want that. It says pour molten salt into water, explosion. Don't want that one. Oops. But you can look up potassium's reaction, but it's going to get more violent. Okay, and I want to actually take that out of here. The alkaline earth metals are going to be the next column over. And so there's some demonstrations here for magnesium in air and calcium in air, or in water. And what we'll notice is with the sodium in the water, I'm going to get my pen here, we saw that it ran around on the top of the water and then burst into that orange flame. Now what will happen with calcium is not the same thing. And so if we look at our link here, there's water, and we're going to add calcium to that.
Water.
And you just see that we make bubbles. So not as thrilling as the sodium was. But if we look at magnesium here, what's kind of cool about magnesium is it burns with a very white flame. So here we have our magnesium and its turnings. So this person is being very thorough. You'll see that it's a shiny gray metal. And there's some magnesium ribbon just to get us a little fuse there. And then we're applying some heat, and once it gets started, you're going to see that it burns with a very white flame here. Instead of orange like sodium, it is white. And so it's kind of cool. This is what's found in sparklers in fireworks. Now group 4 doesn't actually have a name. That is the group that has carbon in it, and we're going to be looking at carbon in more detail later on. But we know that there are two forms of carbon, the diamonds, okay, which are in this form, and then we also know graphite as pencil lead. That's another form of carbon. You're going to see here silicone is in forms like this is sand, but it can also crystallize into quartz. And then the halogens are very reactive. Now, fluorine is a gas at room temperature, so is chlorine. Okay, it's a yellow gas. But bromine is a liquid, a red liquid at room temperature, and iodine is a purple solid. Go figure. But when group 7 elements react with group 1 or group 2 elements, we get very violent reactions. And then group 8A are called the noble gases. And they're called noble, or they're also called inert. Okay, inert. And that means they don't react. Now, the heavier ones will react with some other chemicals, but we kind of have to force them to do that. As a rule, the noble gases tend not to want to react with anyone. Now, the main group elements are found here on the periodic table. Okay, and so groups 1A through 8A are considered the main group elements. Okay, now the main group metals are group 1 and group 2, and then some of these down here. Now, the elements in the middle are called the transition elements. Also, the elements down in the 2 rows at the bottom are also called transition elements. And then each of the periodic table elements can be classified as a metal, a non-metal, or a metalloid. And so you'll see here that on the left-hand side of the periodic table, most all of these elements are metals. On the right-hand side of the periodic table, over here in the yellow portion, these are non-metals. And you'll need to know the chemical and physical properties of metals and non-metals. And you'll see that on subsequent slides. And then the elements in the middle that bridge the gap are called metalloids. Now, this is talking about the metals. So they're solids at room temperature except for mercury. They're shiny, okay, meaning that obviously they are look like a mirror type of thing. They conduct electricity. Ductile means that you can pull them into long wires. Malleable means that you can beat them with a hammer into thin sheets. They can form alloys, two metals at least mixed together. And they tend to give up electrons in chemical reactions. And we're going to see this is going to become important when we look at how things tend to react. Now, the nonmetals, those are things over on the right-hand side of the periodic table, except for hydrogen, okay? They all are on the right-hand side of the periodic table. Hydrogen is considered a nonmetal, okay? They don't conduct electricity except for the graphite form of carbon. And in chemical reactions, they tend to accept electrons. Now, the metalloids are, it's smack dab in the middle, things like arsenic or boron. And these, they look like metals. So you'll see here, this does look like a metal. They're kind of a shiny a little bit, maybe a little dull, but they're gray and they do look like metals. But they don't conduct electricity. Okay, and so they typically are going to have some chemical properties of nonmetals and some physical properties of metals. Like they look like a metal, but they don't react like a metal. And so here they are in the list. And so some people disagree about astatine and polonium, but they're both radioactive, so I don't really care if we accept those as a metalloid or not. Now, this is my favorite YouTube video, and this is talking about how elements react with one another. Hopefully we can get this to go there. There we go.
So there's a regular fund, and then there's a hedge fund, and we hedge it hard.
Zinc will pick out hydrogen. We'll talk about this.
Can't get it now, but I can get up. Can't get it now. I can't get it now.
Neon is a noble gas.
What's up the stairs? What's up the stairs? Can't get it now.
Hydrogen likes carbon, and in fact, 4 hydrogens like carbon. Noble gases do not bond anybody. So in the chemical party, loners. Potassium and water. Alkali metal. Explosive.
not so bad.
So hopefully you like that one. I love that video. But it shows some things bonding together. Potassium and water, explosive reaction. The noble gases don't really like to hang out with anybody at the party. Now, the next section is on ions. This is section 2.6 still on our loveliness. And so what we want to look at here is we want to look at what the elements tend to do when they chemically react. And so where they are placed on the periodic table will matter to what kinds of reactions they have. So an ion, whoops, got to get our pen back here, is an electrically charged particle, and it's from an atom or a group of atoms that have lost or gained more than one electron. And so first of all, we're going to look at magnesium here. And so ions can be formed, okay, by gaining or losing electrons. And so metals tend to lose one or more electrons, and they will form a positive ion called a cation. Now, a cation, if you look at the letter T, it looks like a positive sign, so that's how I know that a cation is a positively charged ion. Now, what you may not consider or think is intuitive is the loss of electrons gets you a positive charge. The positive charge doesn't come from us adding electrons into you. We're actually losing electrons. So let's figure out how this works. So of course, there's a YouTube link that you guys can watch on ion formation. So please do that. It further explains this. But in magnesium, there are 12 protons inside the nucleus. So we've got a plus 12 charge inside the nucleus. And we know that there are an equal number of electrons orbiting around the neutral atom. So each electron has a -1 charge associated with it. So we have -12 orbiting around our nucleus, and we have a plus 12 inside the nucleus. -12 and plus 12 equals 0. And that's why we call this a electrically neutral atom. Now, metals tend to lose electrons, and magnesium happens to lose 2 electrons in a chemical reaction. Now, if it does that, it now has not 12 electrons, but it now has 10. So it has -10 charge orbiting around the nucleus, because each electron has a -1 charge, and there are 10 electrons. So -1, -1, -1, up to the -10. The number of protons, though, stays the same. So we have a plus 12 charge inside the nucleus, but only a -10 charge orbiting around it. So if we add these two together, we're going to get a plus 2. So the 2 electrons have been lost, but the charge on the magnesium then becomes a plus 2. So it has 2 less electrons than protons. And that's why it's a positive charge, because the protons have this positive charge, and if we don't have enough electrons to cancel out that positive charge, we're going to get this cation formation. Now, nonmetals, as we said, the elements on the right-hand side of the periodic table, tend to gain 1 or more electrons, and they form negative ions called anions. So here is the neutral chlorine atom. There are 17 protons inside the nucleus and 17 electrons that orbit around it. So we have a plus 17 charge inside the nucleus and a -17 charge orbiting around it, a -1 for each electron that we have. Now, if we add in an electron to our total, now the chlorine has 18 electrons. So now it's a -18 charge orbiting around the nucleus, and we still have that positive 17 charge in the nucleus for the protons. So if we add these two numbers together, we're going to get -1. So when chlorine gains an electron, it will have a -1 charge. And it can be written like this, or it can be written as chlorine -1. The -1 is saying we have an extra negative thing around, because each electron has a negative charge. And that's why when you're an anion, you're gaining extra electrons, extra negative things, and it makes your charge more negative. So some of our families what charges of ions do they typically make? Well, group 1 typically makes a +1. We can either write it as +1, like potassium +1, or sometimes they write it as 1+. I tend to do this, but there's nothing wrong with the 1+. Group 2 elements make +2 ions, so those are things like magnesium +2 or calcium +2. The halogens make -1s, so like fluorine -1, chlorine -1. And then you'll notice the noble gases, group 8, don't make any ions at all because they don't want to undergo a chemical reaction per se. Now let's look at the periodic table here. The main driving force for someone to form an ion is for them to have the same number of electrons as a noble gas does, meaning it has the same number of electrons physically as a noble gas has, and so the elements will gain or lose electrons to get that. Now, hydrogen, remember, doesn't belong to any family. Hydrogen we have out in our periodic table right in the middle, and normally hydrogen will lose an electron, and when it does that, it will become hydrogen +1. Now, everything in group 1, we said, will make a +1 ion, okay? And the reason for that is, if we look at lithium, lithium normally has 3 electrons. So if we look at the noble gas on the periodic table that comes after lithium numerically, and this is neon, element number 10, in order for lithium to have the same number of electrons as neon does, it would need to gain 7 electrons to get the same number, 10 electrons, as neon has. Well, that's a lot to gain. But if lithium were to go backwards and have the same number of electrons that helium does, and helium is atomic number 2, lithium would only need to lose, so here is helium, that has 2 electrons. Lithium would only need to lose 1 electron to have the same number of electrons that a noble gas has. And so this is what it does. If it loses 1 electron, it will get a +1 charge then, because there's an extra proton and 1 less electron. The same thing happens for group 2 elements. Group 2 elements tend to form a +2 cation, and again, the reasoning is the same. Magnesium, if it wanted to have the same number of electrons that argon has, magnesium normally has 12 electrons, okay? And if we're looking at argon here, argon typically has 18 electrons, and so magnesium would have to gain 6 electrons to have the same number as the noble gas that comes after it numerically on the periodic table. But if it were to go backwards and have the same number as the noble gas that comes directly before it, which would be neon, neon has 10 electrons. Magnesium has 12, so all it needs to do is lose 2 electrons to have the same number of electrons that neon has. So magnesium would have become a +2 ion. So everything in group 2 has a +2 charge. Guess what? Group 3 elements will have +3 charges. Now, group 4 is going to be either a -4 or a +4 because this is the middle of the road. It can either gain 4 electrons or lose 4 electrons. So it's the middle of the road. Now I'm going to get rid of all the ink on here because I need to be able to see this. So this could be a +4 or a -4. Whoops. Now after you get past group 4, now we're closer to being like a noble gas. We have element number 10 here. So if we look at nitrogen, it's element number 7. And so here we have our helium, which we were dealing with before. If nitrogen wants to become like neon, we have 7 electrons in nitrogen, 10 in neon. It only needs to gain 3 electrons. So it needs 3 extra electrons. And so it's going to have a -3 charge. 3 extra electrons are shoved on there. Because if we were to count backwards here, and nitrogen, if it were to lose electrons to have 2 like helium, it would have to lose 5 electrons. It's easier to gain 3 than lose 5. Okay? Now group 6A elements, so this has 8 electrons, oxygen does. It only needs to gain 2 electrons to be like neon. That's easier than losing 6 to be like helium. So oxygen is going to want to gain 2 electrons. And in fact, everybody in group 6 is going to want to gain 2. So they'll have a -2 charge. So sulfur will be a -2, selenium will be a -2. Now, hydrogen here, if it gains an electron, will have a -1 charge. Again, if it lost an electron, it would be +1. This is usually what it is a +1. But here's fluorine. Fluorine has 9 electrons. It only needs to gain 1 electron to be like neon. Now, it doesn't become neon because it still has 9 protons, but it will gain 1 electron to be like neon instead of losing 7 electrons to be like helium. Going from a 9 down to a 2 means you would have to lose 7. So it's easier just to gain the 1, and that's why halogens have a -1 charge. This is really important for you to know, is the charges of these elements in these families, +4, -4. If you can't remember them, put them on a note card, but you're going to need to know this information. Now, what we'll find is that if we look at the next section here, it says a certain ion contains 54 electrons and 78 neutrons. It says, what is the mass number of this ion? Well, first of all, it says it has 78 neutrons. Okay, so we know that's going to be part of the mass. And so we have to figure out how many protons there are in this ion. And this ion has a +1 charge. So has it lost electrons or has it gained them? Hopefully you said it lost them. So it's lost an electron, and it actually lost 1. So originally it had 55 electrons originally, which means it has 55 protons. So 55 protons plus 78 neutrons is going to get you 133 as your mass number. Yay! So just be aware that a positive ion means you have lost electrons. All right, so that's it for section 2.6, and we'll come back and finish off our last section, which is last 2 sections, which are 2.7 and 2.8. Thanks for listening.